Hey, Simon. Thanks for bringing me to this fancy new seafood restaurant. What's it called again?
I told you, Gaga. It's called the Poisson.
Wait, did you say Poisson? As in the Poisson model of mortality, one of the three main actuarial mortality models, along with the Markov and binomial models?
Well, I thought it just meant fish in French.
Oh, Simon, let me explain it for you. The Poisson model is used to model the number of rare discrete events occurring during a period of time. Actuaries use it to model the number of deaths occurring amongst a group of lives. Given the time spent exposed to risk, they can find an estimate of μx, the force of mortality.
I know what μx is. It's the instantaneous rate of mortality at a moment in time. μx equals the limit as h tends to 0 of 1 over h, hq, x.
Good. You know more about mortality than I thought. Do you remember the probability function for a random variable x with a Poisson distribution with parameter lambda?
Yes, the probability that x equals e to the minus lambda, lambda to the x, over x factorial.
Great. And the mean and variance?
They both equal lambda.
Excellent. So let's use what you know to construct a model for the number of deaths in a group of lives, given the observed waiting time, or exposed to risk, exc. Let's assume we observe n people and that the period of observation is sufficiently short that the force of mortality mu is a constant. Then the mean number of deaths over the observed time period will be the force of mortality multiplied by the exposed to risk, so lambda e equals mu exc.
I see, so then we can substitute that into the Poisson distribution formula, meaning the probability of observing d deaths equals e to the minus mu exc, mu e, xc to the d, over d factorial.
Simon, you got it.
Well, that's okay in theory, but how does this apply to me in the real world?
Okay, as an example, let's consider the number of diners who die after eating bad clams in this restaurant. I spoke to the chef and he told me that 2,000 diners have had the clams since this restaurant opened. Let's assume they experience a constant force of mortality of 0.0009 per year. If we assume deaths are independent, then we can calculate the mean number of deaths in the next year by lambda e equals mu exc, which equals 1.8.
So, 1.8 people will die after eating the clams.
Well, it's not certain that anybody will die. We can calculate the probability that everyone survives the clams by substituting d equals 0 into our model. So the probability of no deaths equals e to the minus 1.8, which is 17%.
That's not very reassuring.
Well, I just used an estimate for the force of mortality, so if it's lower than I thought, then you've more chance of surviving.
Okay then, so what if I want a more accurate estimate of the underlying force of mortality, given the observed number of deaths and the total exposed to risk?
We can do that too, by finding the maximum likelihood estimator of mu.
I know how to calculate MLEs. You take logs of the likelihood function and maximize by differentiating with respect to the parameter and setting equal to 0.
That's right. For the Poisson model, the MLE from mu turns out to be d over exc.
But isn't that the same MLE for the two-state Markov model?
Yes, it is. In fact, the Poisson model approximates the two-state model, unless the waiting times are fixed in advance. But this isn't an exact model since it allows a non-zero probability of more than n deaths. Though in practice, unless n is small and qx is large, this is not a serious problem. It also assumes that the central exposed to risk is a fixed amount, and that the force of mortality is constant between ages, which aren't always reasonable assumptions.
Oh? Are there any ways we can adjust the observation to make the Poisson model exact?
Yes, we could continue the observation until the waiting time reaches a predetermined value, and we could replace each death with an identical and independent life at the exact moment of death so that the population size is kept constant.
That sounds complicated.
Yes, that's why Actuaries prefer the simpler model.
What about multi-state models? For example, people who get sick after eating the clams rather than dying.
The Poisson model extends easily to deal with multiple decrements, but not to processes with increments.
Wow, Gaga, you've taught me a lot about the Poisson model of mortality. Now I'm hungry, and here comes our meal. What did you order?
The clams.